Hi, my name is Jennifer Thompson and I'm one of the CWT partners from IBM. Welcome to today's session, which is titled Understanding 5G, which is going to be hosted by Clare Somerville from Intel. Before we get started, I just wanted to let you know that we will be recording this session. So if you have any concerns about that, please log off now. Because the event will be recorded, we'll be posting the replay link after the event. And if you're listening to the recording now, thank you for listening. So just to remind people, CWT Partnership stands for Connecting Women in Technology, and we've been in existence for a number of years. This week, we're hosting our CWT live event, which is typically in person, but is a great opportunity for us to go live via a virtual platform across 4 days, offering a different event from each of our partners. The partners that make up the CWT sort of model are Avaya, Dell, HPE, IBM, and Intel. If you're here with us today or listening to the recording, we encourage you to listen to the other events or join us live by registering for anything later on in the week too. So for those of you that are with us live, you will be off video and on mute. That doesn't mean you can't speak to us. You can do that via the chat facility in the right-hand side of your screen. You'll also see some polls running through the event, so they will pop up and we encourage you to vote to engage in those questions. There's also an Ask a Question feature within the system, again, towards the bottom of your screen. And we encourage you to ask questions here, which we will cover in a Q&A session towards the end of the event. These don't have to just be for Claire, our speaker. You can do the questions for others to ask in the group as well, but it just spreads out chat to questions via the two different functionalities within the tool. I'm going to go off video in a minute as your facilitator, just to help with the streaming and leave Claire as the primary video on screen. However, you might see me jumping in and out as we run different polls or have any questions that we need to cover. So I look forward to seeing you again, either in between or at the very end. And I really do hope you enjoy the session. So with that, I'd like to say thank you very much to Claire for being with us today. And we'll hand over to her for her introduction and to talk to us about 5G. Thanks, Claire.
Great. Thanks, Jen. So hi, everyone. Good morning. I'm Clare Somerville. I work for Intel in the UK in the area of 5G mobile networks. So as Jen mentioned, today what I'm going to do as part of the CWT live event is give a tech talk on 5G. So it's going to be quite a high-level talk. I'm really just going to keep to the very top level information, but I'm hoping that at the end of this talk today, everyone's going to come away with a better understanding of 5G. So if you do have questions, then please do use the chat window, the Ask a Question window, and I am going to then take those at the end of the talk, primarily because I can't see any of that information at the moment, so it's just going to be easier if we just save all of those questions till the end of the talk. So to start with, I would be interested in starting with a poll. So to help me sort of gauge people's engagement with 5G, it would be great if you were able to sort of let us know with a poll, Jen's hopefully popping up. Do you have a 5G mobile phone? So a simple sort of yes or no. So maybe if I give everyone sort of 30 seconds to a minute to decide if their phone is 5G enabled, that would be great.
So I can confirm we've got votes coming in thick and fast already, Claire. So they're just bumping around the numbers. So like you say, let's just give it another minute or so, and I will let you know how the votes have been cast.
Oh, great.
Okay, it's kind of slowed down now. So anybody on the line, if you haven't yet voted, please look for that poll menu in the bottom of your screen, and it should give you the option to vote. Great. So at the moment, we've got 3 for yes and 12 for no.
Right. Okay, so I'm now doing my maths, and I guess that's 20% is a 5G mobile phone?
Yes, it's 20%, correct, and no is 80%.
Right. Yeah, so to be honest, that's actually higher for the 5G mobile phone than I was expecting. So I guess maybe that's representative of the fact that we all work for technology companies. So I do myself have a 5G mobile phone, and the reason why I have one is last autumn my 4G phone needed to be an upgrade, so running out of memory, battery running down, and because I worked in the industry, I went and looked specifically to see if I could get a 5G phone. And every model, every sort of manufacturer had one. So my preferred manufacturer did offer a 5G phone, but I think they had like 8 or 9 4G variants and only one 5G variant. And so that is kind of representative of where we are today. That you can get mobile phone 5G phones, and price wise for your they're not really costing much more than a 4G phone would. But they are something that you do have to actively go out and search for. I will also own up to not having any 5G coverage in my house. But when I do go to London or I go to somewhere, other cities around the country, then I get a good 5G service, and I'm pretty happy about what I'm getting quality-wise in 5G at the moment. So yeah, I mean, it would be interesting maybe in that chat window at the end, if anyone else did have a 5G phone, if they've found a really good positive, what kind of experience they've had from it. That might be interesting for someone to add to the chat window. Okay, so for the talk today, what I'm going to cover is I'm going to look at why we need 5G. It was about 5 years ago now that we started really having a lot of the hype about 5G and what it was going to do for us and how it was going to help us as a society. So now we're coming to these early deployments of 5G networks, and they're starting to expand. It's a good time to recap on what it was that really motivated us to create 5G networks. Which ones of those hypes came true, and which ones maybe just disappeared. Then I will kind of give an overview of the key technologies and trends of 5G. So what are those technology improvements that we need to do to enable us to build out those 5G networks? One of those is virtualization, and I'm going to give a little bit more of a deep dive into that, and specifically the virtualization we're doing in the radio access network. So in 5G, the radio access network is basically the cell sites, those towers that you see everywhere. At the bottom of those is a big green box, and that holds the 5G radio access network. The reason for focusing on that a little bit more is I think that every company that's part of CWT is involved somehow in that activity. And that activity is completely hidden from subscribers. They wouldn't know anything about virtualization, but it is having quite a fundamental shift in the way that we're building out 5G networks. So why do we need 5G? So for this, I think we really have to do a recap of the history of mobile communications and where we are. So if I go on the left, back about 25 years ago when we started having our 2G networks, and 2G networks were all about voice. So before 2G, if you were going to meet someone, you had to plan what time you were going to meet them, where you were going to meet them, arrive there, and if the other person is late, for example, the train or bus was late, you just had to wait and see if they were going to turn up. So obviously 2G added the mobility. It really made us be able to be more relaxed about our arrangements, be more spontaneous. So that's kind of popular, and it really sort of helped us kick off a good solid start. And it also helped that it was the same technology that was used in most of the places around the world. So that mobility was truly mobile. It is interesting to note that 2G did actually have a data service. So the very sort of early data service were 9.6 kilobits per second. So that was exactly the same bandwidth that you could get to your home at the time. And if you have a smart meter for your gas or electricity at home, then that is using actually 2G to connect and send data back to your energy supplier. So 25 years later, 2G is still here and it's still being used. So if we then move on to 3G, 3G was designed and defined to be both a data and voice network. But at the beginning, it very much was voice orientated. And if you did use data and people were struggling to find out a reason why you would want to use data on 3G, you were typically just sent to sort of a closed environment to use the sort of apps that your service provider kind of opened up to you. So for quite a while in those early days of 3G, it was really all about voice. And then what happened is we got the iPhone, so the the start of the smartphones that we know today. And suddenly everyone had a device that was easy to use, and it was great and a purpose to go and generate data from. So we suddenly started getting lots of data on our network, and a lot more data than voice. And it very quickly became apparent that 3G really wasn't designed for the amount of data that we were getting through the network. And that was our motivation for creating 4G. 4G was a data network right from the start. So everything about it is designed very, very much for sending data. And for quite a long time, and possibly even today, if you make a voice call on a 4G phone, you'll actually quite often just drop back to the 3G network to make that voice call. So 4G is all about data, and it's worked well for data. So as data has continued to increase, then they've introduced new features to 4G to handle the more data. What that tends to happen is that then we get more data. So we just have this constantly increasing cycle of data and the need to support it. And so our motivations from 5G, now moving to the right-hand side, really is to handle that data. And so as well as getting more data, we're also finding more things are generating data. So instead of it just being people and their smartphones, we're now getting that Internet of Things, machines generating data as well. So 5G is very much about supporting the data and supporting more things generating us data to our network. So if I just talk about those things that are going to be generating our data for 5G. So in the left-hand box, we've got sort of people and smartphones. And here, the data that we're creating and why we're generating so much of it really comes down to one word, and that's video. And we're streaming more of it. We've got YouTube, we've got TikTok, we've got Netflix, and we want to stream that everywhere. And so that is really making our data explode. And we're starting to stream more high quality video, and that again is making our data explode even more. So there's a really, really strong need with 5G to just handle the amount of data that that we're creating via our smartphones. So the middle one is our first look at how we can move 5G to a sort of a vertical segment. And so here we've got a very expensive looking machine on some kind of production line. So these machines have got quite unique characteristics. So if it's important that the connection that we have to it is very reliable. If it's running on a kind of industrial environment, then it's got to be very reliable, that data, and it's also going to require low latency. So that's got quite specific requirements, and so we need 5G to be able to support those specific requirements. If we move to the right, we then have kind of the opposite type of machine. So here we're talking about a small machine that's a small device that's just designed to do one thing, but there will be many, many of them. So if we want to be able to use 5G to support that, then what we need to do is to be able to handle billions of them. So just having that capacity to handle lots and lots of devices within our network. And that's an opposite challenge from the other two, but it's still a challenge. So as a recap of where we are today. So everyone like myself who's got a 5G smartphone, our smartphones are going to be running and supporting what's called Release 15. So that was standardized, our standardization body is called 3GPP. And at the end of 2018, they defined and released what was the first version of 5G. And that's what's used in networks today and used in the smartphones today. At the end of last year, they defined the second version, which is called Release 16, and that's got the additional features to handle those smart machines. So it's got the introduction of this feature called URLLC, and that stands for Ultra Reliable Low Latency. So it does the reliability and the latency aspects I mentioned that you need for 5G in a sort of smart industrial environment. At the end of this year, they then plan to release the third version, which is called Release 17, and that is designed for the billions of devices. So it's got the features and capabilities in it for us to scale something up for many, many devices. So that won't be the end of 5G. 5G, the way it works is that we'll continue to have sort of releases at regular intervals, and each of those will sort of improve things and add more features. So it's a living standard. It's not something we define once and then leave, but throughout its lifetime, it will continue having variations and improvements. So I do want to touch on something else that's new in 5G compared with our past mobile networks. And that is really this expansion into very much having a concept of a public network and a private network. So a public network is really what we all know. So 2G, 3G, 4G, 5G on our phone, having it with a service provider such as Vodafone or EE, they're providing a public network. So they own the network, they will manage the network. It covers a wide area, so it covers us all across the UK. We can roam when we go abroad with it, and that is always typically done on a dedicated licensed spectrum. So they paid from the spectrum and the rights to have that network and provide that service. On the right-hand side, we've got a private network. This is something that does exist already, but is expected to be a lot more common with 5G. And so here it's talked about an enterprise-owned mobile network. So examples of this might be a factory. So a factory who wants to provide a service, they would want to create a private network. They might manage it themselves. They could hire a third party to manage it, in the same way that lots of companies outsource their IT. It would have just a targeted coverage area. So if it was maybe a university or company doing it, it would cover their campus. If it was an industrial company, it would just cover their factory. So it's not a wide area network, it's just very specific. And the key thing there is that that's just for them and for a subset of, and only the mobiles that they're really allowed to connect to use that as a network. In the middle, we have what's called hybrid. And so this is just really acknowledging that you can have a concept of public and private. A really good use case of that, I'm going to give a bit more detail on later, might be a sort of a stadium scenario where you need some parts to be private to, say, run the facilities of the stadium. But when you have people coming in for an event, they obviously want to watch that event and be able to connect and send things to social media across their standard service provider. So a hybrid is that sort of mix of private and public, and that's this is something that's a lot more common as a concept of splitter networks in 5G. So again, focusing on what we need and why we need 5G, and here and that's very much I've mentioned about data growth. So we have a couple of industry reports that are produced regularly. One is by Ericsson and one is by Cisco, and they kind of use their experience to look and see what is happening in mobile networks today, and then they project that going forwards. And they've been doing this for several years. So the top set of data comes from the Ericsson Mobility Report, and they call out the number of subscriptions that you have that exist for mobile networks across the world, and also the amount of data per month that's generated. So if we look at subscriptions first, then we see that about 5 years ago, there were 7.4 billion subscriptions across the world. Today, it's 7.9, and in 5 years in the future, they're expecting it to be about 8.8 billion. So we see that there is an increase in subscriptions, but actually that's not a particularly large increase in subscriptions. And the reason for that is just that nearly everybody already has some kind of phone, so a mobile phone or a smartphone. So there's not really very many more people to sell subscriptions to. So that gives some of the motivations why it's great to have machines connecting, because machines can also be subscriptions. But overall, our subscriptions is staying pretty steady. Now, if we look at the next one down, this is data per month. So these numbers are given in exabytes. So an exabyte's 10 to the power of 18. So as a comparison, megabits per second is 10 to the power of 6, gigabytes 10 to the power of 9. So an exabyte is a significant amount of data. And about 5 years ago, across the world, they were generating 5.4 exabytes per month. Today, it's 10 times that, so 51 exabytes per month. And going forwards, it's expected to be 5 times again, up to 226. So that is a huge growth in data, but there's not that huge growth in subscriptions. And if you think about the kind of mobile phone package you've had, the amount that you've paid over the last 5 years hasn't increased tenfold. So we can see that there's a challenge, and there's a challenge to just handle more data per subscriber, and the subscribers aren't necessarily going to pay for all the extra data they're generating. So we actually need to handle that data in a more efficient way, more cost-effective way, and that's a big part of 5G. And virtualization is helping a lot with that. Is how do we just make our networks more efficient? I did call out some UK trends from the Cisco Internet Report. So they projecting that in 2023, our average start speed will be 86.8 megabits per second. So that's comparable or more than the kind of broadband you have at home. And interestingly, they also said that in 2023, 5G will be 19.5% of total mobile connections. So at 20% today, in that poll at the very beginning, we as a group are already sort of exceeding that. So it will be interesting to see whether it's just because we all kind of work in technology and maybe more interested in having up-to-date technology, or whether actually the uptake of 5G will be faster than expected. Okay, so the next one is I talked about the industrial and the need for 5G within that industrial environment. So in the box at the bottom, I talked about the kind of reliability required. So here we've got what that reliability definition is, and that translates into if you send 10,000 packets, we need 9,999 of them to be successful, and one of them can be sent in error. So that's challenging to do, and 5G has to have particular techniques available to help us achieve that kind of level of reliability. From a latency perspective, here we're talking about being able to have a latency of less than a millisecond. So again, that's challenging and something that we have to sort of build into 5G to be able to support it. Yeah. So the key motivation for and sort of requirements for industrial are these private networks, the ultra reliability and the low latency. The kind of opposite of that is there's quite expected to be quite a lot of video kind of scenarios within a factory of streaming what's going on in monitoring video cameras. And quite an important one is the bottom one, where it talks about security and privacy. And that's that if you are a company with highly important and critical data, sometimes you don't want that data to leave your site. And so we have to be able to do almost a complete 5G network on site to ensure that industrial company can keep their access and their data are private and on-premise. So the third one was that billions of devices, and here there's a lot of scenarios and trials going on to do with smart cities. The city of Dublin in Ireland has had one running for a couple of years, and they've been doing lots of experimentation about what they can do with small devices to really help improve the city, so make it more sustainable services, kind of improving public safety, helping with environmental issues, and sort of reducing costs. So it's about making people's cities more livable. So the kind of requirements that we have here are in the box at the bottom again. So a lot of these devices are running off battery, and they've got a 10-year battery life. So that's pretty similar to say a smart meter we have at home. So the gas one typically has a 10-year life, and it has to run off battery. It needs to be wide coverage, so it can cover an entire city, and it doesn't matter where that device is. And because of that wide area coverage, quite often people are doing these on public networks. And the kind of devices that ultimately they're looking at making we can support is up to 1 million devices per kilometre squared. So we're nowhere near that value at the moment, but that is the hooks are being put into 5G so that we are capable of reaching that density if it's required. So on this, I did just put a picture of a kind of street lamp and all the things that people thought that they could add on a street lamp and maybe connect via 5G. And the first thing to note is that street lamps are starting to become really important in cities. So when you're trying to look and put all this infrastructure around, then there's not very many places that you can actually put that infrastructure. And so street lamps are there, and so they're actually becoming quite a really important part of real estate for 5G. And the kind of services you can get from it is you can have a wireless transmitter, so providing what's called a small cell, all the way down to environmental things such as detecting water, or if you live in the right part of the world, seismic centers for sort of public safety. Right. And then just adding a fourth one in there, and that's a smart venue or smart stadium. And I sort of touched on that in the beginning as being a good example of what can be a hybrid network. So here we just we have parts of that are related to the operation efficiency. So you can have heating and ventilation, you can have smart lighting. These are just the facilities that help the stadium to run, and they need to be there and all the time. And then at the bottom, when we have an event coming on, the fans come in, they want to have a good signal. They want to be able to use their own network to do that, to upload something to social media at halftime, those kind of effects. And so they need to have that public network. Here we can also talk about a concept in 5G called network slicing. And so network slicing essentially means that you can sort of have you can take some aspects or some things running in your network and give it a certain type of quality of service, or reserve a certain amount of your network for that group of devices in a network slice, and then you can have everything else in a different network slice. So the smart venue is a good example of that. As you can see that we've got these boxes in purple that are our operation efficiency boxes, and we need those to run all the time. And that's probably fine when the stadium is empty, but when the fans turn up and they start generating lots of data, and it's football at the moment, so there's a half time, and then that's when they want to upload all their photos to share what they've just seen. So we get a big spike in data requirements, and network slicing is something that can ensure that all that extra data that's coming through doesn't interrupt or stop that operational efficiency of the smart venue. So mixing all these types of devices together, network slicing becomes an important part of 5G to enable us to do that. Okay, so I was going to talk about the key technology trends of 5G. So this can kind of be summarized in 4 blocks. Is 5G introduces the ability to have more frequencies. So I'm talked a lot repeatedly about the data problem. And so if we need to send more data, then one way we can do that is we can have more frequencies. So each frequency is kind of a pipe that we're sending data down. So if we have more frequencies, we have more pipes and we can send more data. There's also a concept which is new in 5G called massive antenna arrays. And this basically just means that in a particular frequency, we can send more data. So those pipes that are sending data effectively become thicker. So we can just they become wider a lot, and then we can send more data down them. So on the right-hand side, we've got ultra-dense networks, and this means that we basically shrink the size of our cells, and we have small cells, and if we have more of them, so our number of cells we have become denser. And that means we're repeating our frequencies more. So again, if we repeat the frequencies more, we can send more data. So those 3 critical technologies are all about us being able to get more data into our network. So the 4th one, the network function virtualization, this is about managing that data. So once we've generated all that data, we need to be able to manage it more efficiently. And it's network function virtualization that enables us to do that in 5G. So looking at the frequencies, so first of all, I've kind of got that line down the bottom, and it's worth explaining that on the left-hand side, where we've got sort of low bands, any frequency in that range, it will travel quite a long distance, so we can have quite large cells of several kilometers in size. But each frequency is quite small. So at 600-700 megahertz, we might be able to have a frequency band of, say, 5 megahertz. So we can send, we can have very, very large cells, but the amount of data we can send in that cell is actually quite small. When you move to the right-hand side up to those high bands, well, up there, our frequencies don't travel so fast, so we end up with small cells, and here a cell size might be just a couple of 100 meters. But the frequencies up there are much larger, and we can so we might be able to have, say, 800 megahertz of bandwidth for a particular frequency. So we've got small cells, but we can actually send a lot of data in that small cell. So so there's kind of pros and cons of both low bands and high bands and where you transmit on. So today, 2G, 3G, and 4G, I've highlighted where that is. So that's very much to the left-hand side of the diagram. So we have quite large cells, but the amount of data we can send in them is quite small. So 5G opens up all these different bands. So there's going to be 5G in low bands, in mid bands, and high bands. And that's a key part for us being able to put more data through our network. I've highlighted what's called the 5G sweet spot, and that's in the mid-band section. And that just happens to be an area where we can have quite large, fairly large cells, so 2 kilometers in size, but we can actually send more data. So here, the channel bandwidth could be up to, say, 100 megahertz. So 2G, 3G, and 4G typically goes up to 20 megahertz in bandwidth, and whereas this 5G sweet spot is 100 megahertz of bandwidth. So immediately you could get 5 times more data through 5G. In terms of public and private networks, I've talked about the low bands and mid bands are predominantly public, and that's because they're quite valuable because they can travel quite far. So that tends to be licensed spectrum that's paid for. And when we get up to the high band, that can also be licensed, but that tends to be where you might have more private because there are more opportunities for having unlicensed spectrum up in that high bands. So the second technology is massive antenna arrays, and that generates us more capacity per cell. So there's a lot of complexity behind that. So I'm just at a really kind of high level summary. What matters about it and what it does is that in 4G you could kind of look at a base station and see the antennas at the top of it, and imagine and they would just really transmit evenly throughout the cell. So they what happens in 5G and what these massive antenna arrays let us do is they let us do a technique called beamforming, and that basically shapes what we're sending. So it shapes a beam to each user. And so if we shape what we're sending and we send a dedicated beam to a specific user, we can do that more efficiently. So we can get more data to that user, and that increases our overall cell capacity. And actually, if we want to get the full maximum cell capacity we can in a 5G network, we have to do that with 4 beams simultaneously. So at any point in time, we've shaped these 4 beams at our antennas, and we're sending data to 4 different users at the same time. So there's quite a lot of work and effort behind making that technology work. Okay, so for ultra dense networks, we talked about these being small cells. So a small cell really does what it says. It just lower powered. It is a couple of 100 meters in size, and if we repeat those a lot, then we can have more data into our network. So those tend to be used in dense urban areas. So as an example, the City of London already kind of does this for 4G. But as we're going to the 5G era with more and more data, we're going to see more scenarios and more places where we're actually having small cells and lots of them to just handle the amount of data that we need to do. So if a small cell is only 100 or 200 meters in size, then if you were in a car, you wouldn't stay in that cell for very long. But what happens is that data in our networks, it predominantly comes from people that are actually stationary. So they're sitting having lunch or coffee, or they're slow moving, such as walking. So that makes small cells quite useful for handling a lot of data, because people that are sending lots of data are typically stationary, and so will stay in that small cell for quite a while. Okay. So the fourth one, and the one I'm going to give a little more in depth into, was this virtualization aspect. And so now I've explained how we're generating more data. We need to handle that data in our network. Okay. So first is, what is virtualization? So I think every company that's part of CWT does something about virtualization. So there might well be people listening that know a lot more about virtualization than I do. Equally, there might be some people who've never heard of the term. So at a just really, really high level, the objective of virtualization is to improve scalability, so we can manage lots of instances of something. We also want to reduce costs with it, and we want to standardize our software deployments. So all of that just makes a network or makes easier to manage. What it does is it achieves this by creating an abstraction layer between the software and hardware. So on the left-hand side, we've got a virtualization system, and that introduces what's called a hypervisor. And the hypervisor is a piece of software that provides our interface between the virtual machine and the hardware. So the hardware is storage, so hard drives, compute, so the CPU, and I/O, so your sort of Ethernet Wi-Fi connections. And then inside each virtual machine, we have an operating system, the OS, and we have different applications. And then the box down the side is called orchestration, and that just really manages our network. So it's a way of just splitting a platform into software components and hardware components. On the right-hand side, we have what's called containerization, and this introduces a container engine or a Docker engine, and that's essentially a piece of software that provides the interface between containers and the OS. So you can see the difference here is that on the left-hand diagram with virtual machines, each virtual machine has a different operating system instance, whereas with our containers on the right, we just have one. So in actual fact, in most 5G networks, people tend to be using this containerization aspect. And that's very much true for the radio access network part. And that's really just because if you've got to repeat multiple instances of OS, then that's going to consume more of your platform. So we happen to be suitable in 5G to just have one instance of OS, and then we can have more space for more containers. Okay. So looking at across a 5G network, so we've got on the left-hand side sort of the way that we're connecting to the network. So we're connecting via many different ways into a network. We might be doing it from like an enterprise, so from an office, from a factory. We could be doing it from our home. We could be doing it from small cells, or we could do it from macro cells. So we've got various different ways of getting accessing into our network. And then we go through places where we could just combine those access points. So they're typically called like central offices or regional central offices, and they finally end up at the core network. And then the core network would send our data typically off to the cloud to do some kind of processing. So what you see is that as we move to the right-hand side, all those little icons and pictures start looking more and more like servers, and that's because that tends to be what they become, more and more like servers. So as we move to the right, we start looking more and more like the cloud, more and more like a data center. So actually, the virtualization aspects are much more mature for that part of 5G, as there's a lot of reuse that we can take from what happens in data centers. But when we look at the access part, then those icons start looking a little bit different, and so there we've got more challenges to actually have sort of virtualization. So I've got another poll which Jen can share, and that's I'm just kind of as an experiment. I was interested to find out how many people could guess the number of base stations that are in Vodafone's UK network. So I've got three choices: 7,000, 21,000, or 35,000.
Great, the poll is live and we've got a few votes already. So once again, we'll give it a bit of time to allow people to cast their votes. So just to let you know, Claire, there's been a few questions. We've got 5 in the Ask a Question section. So I know we said we'd cover that when we got to the end of your presentation, but just giving you a heads up for timing. We'll see if we can get to all of those and any more that come in before the end of the session.
Great. Okay, thanks, Jen.
Okay, votes have slowed down. So we had 1 vote for 7,000, so 6.7%. With 7 votes on 21,000, giving us 46.7%, and 7 votes for 35,000, another 46.7%.
Right. Okay. So if I just jump to the next slide, So we'll see that the right answer there was 21,000 sites. So they've got, and it's called 21,000 sites for their 2G, 3G, 4G, and 5G network. And what you'll actually find is nearly all of those sites will have 2G, 3G, and 4G all on them. So a site is an important piece of kind of real estate. And so that means that all the different technologies would typically go at each of those sites. On the right-hand side, I've actually got then the core network. So on the Vodafone, got a basic guide to their network webpage. They just describe it as being several data centers, but each data center capable of 700 gigabits per second. So what you can see from that is, the core network is effectively a data center, and that's the first location in mobile networks for virtualization to be implemented. They're handling lots and lots of data, but there's only a few of them. When we come to the access sites, it's going to be more challenging to virtualize, and I'll explain why next. But because we've got 21,000 sites and a high number of sites, then there's actually a good benefit from solving that virtualization challenge for the radio access network for the RAN. Okay. So the reason why virtualization at the RAN starts being challenging is that the legacy, so that's kind of systems that are there today for 2G, 3G, and 4G, they're typically built on custom proprietary hardware. So we have sort of customized, dedicated types of processors. They're called DSPs, FPGAs, ASICs, and they will run a lot of the RAN. And so that tends to be, it's very customized. It's not something that's used to working with virtualization. So that's sort of immediately challenging to virtualize that. So if we want to move to a virtualized network, then we actually have to transition that custom proprietary hardware into something that's software defined, open platforms, and you can have virtualized containers. And that really means that you end up transitioning from sort of custom hardware to off-the-shelf hardware. And off-the-shelf hardware really means sort of general purpose processors, such as CPUs. So the reason why we haven't done that so far, and the reason why that is challenging, is looking at what kind of processing goes on in the RAN. So there's a network stack on the left, and what you see is at the top of, as you go up the network stack, and at the top of it, the software starts getting more complex. So you end up having more lines of code written, and more complexity in the different paths you can take through the software. But that's actually got quite low to modest processing requirements. Now, when we get down to the bottom of the stack and we get down all the way down to that physical layer, the layer 1, the software complexity is a lot less, significantly fewer lines of code. But what we're doing is we're having to execute that and run those lines of codes many, many times. And that translates into huge data processing requirements. So on those kind of legacy networks today, then layer 2, and above, that was kind of already being run on general purpose processors. We could already handle that. But that layer 1, that was what required those hardware accelerators. So when we're shifting to a virtualized system, what we've had to do is we've had to shift that layer 1 processing to run on general purpose processors. So we've got to be capable of handling that processing, which is called signal processing. So that has been done for 5G, and there are networks that are out there that are commercially deployed that are running virtualized and running all of that processing, including the layer 1 on it. So some of the additional kind of motivation for doing that is that I've talked a lot about the expansion of 5G. I talked about it going into industrial. I've talked about it being large cells, and I've done small cells, being a sort of hybrid model, having this network slicing aspect. So very much going forward with all that expansion of 5G, we've kind of moved away from the fact that you can have one solution that fits all. And so if you've got customized hardware, then it's easy to build a customized hardware for one solution, and it's harder to do it for many solutions. So this virtualization aspect is also useful for being able to adapt more easily for the many different types of networks that you would have with 5G. So here it's just really calling out that we've got sort of different types of access networks, and then we've got different types of edge networks. And edge networks typically would mean that you've got a whole network sort of on the site, and so that again now can all be run on a single virtualized platform. So we're not just stopping at virtualization. Going forwards, the next step and where we want to go with is cloudification. So the difference between virtualization and cloudification is that we really want to have the RAN part, the base station part, so all of that layer one processing, just looking like another kind of container within a platform. So it's not a platform that's dedicated necessarily to 5G, but it just becomes another workload. And effectively, can you make it being run as a service? So that's sort of the next sort of evolution and challenge that we have. And that, again, is just all about being able to make handling all this extra data more and more efficiently. Okay. So finally, as a kind of last slide, having given a talk all about 5G, I thought I'd mention 6G and just like make people aware that the planning has started for 6G already. So we're just at the stage where people are now actively deploying 5G networks. And in the industry, there's already sitting there and thinking about what do we need to do for 6G. So there's within the EU, they typically have all these various research projects. They had a whole load of them for 5G that were very influential. And so their flagship one for 6G's now started and is called HexaX. And that's a 2.5-year project with 25 participants across industry and academia. And so when that completes in about 2.5 years, that's when we'll start seeing a really good idea what people think 6G will be. And that's probably around about when all the 6G hype will start building up. Okay, so that's it for the slide part. I'm just going to stop sharing so I can come and see the questions that have been happening during the talk. So Jen, I'm not sure if I can see the questions or.
Oh, really?
Oh, no, I can.
You can. So anything that's been posted in the chat as a question, I've converted it across. So you can just go through those 5 in Ask a Question. And then if you've got time, there's some just general comments in the chat, but I thought that might be easier.
Okay, so the first question I've got is, it strikes me that the link between the services we consume, the billing and revenue recognition needs to be more timely, more transparent. Any opinions? So I think my view that is I think the trend is actually in some ways more to the opposite. We kind of in the fact that we just pay for a package, and you typically don't expect to exceed your package per month. So it's kind of following that trend to subscription services that we're seeing everywhere, is that you just pay a fixed amount per month, and that usually meets all your needs. So certainly the networks do that kind of billing instantaneously, and that capability would be there. But I think that the trend that we're going just generally is more towards just subscription, and you pay and then almost forget about what you use. So the next question we have is, what elements of 5G do you think will prove most useful in the build back from COVID-19? Yeah. So I think for us after COVID-19, I think there's 2 aspects to that. Is I talked a lot about 5G and how we're wanting to expand into those vertical segments. So I think that's going to be really useful and helpful. So both whether you're helping enterprises to do something more efficiently with the kind of aspects I talked about for industrial 5G, or whether we're actually just talking about things like smart cities and making cities more livable and more sustainable. So there was in the UK, we've had there's been a lot of press about people wanting to move out of cities and more into the countryside, thinking they're going to commute. So if you do want to get people back into cities and you want to have people back into their offices, then I think the better you can make that as an experience, the more likely people are going to want to come and do that. So I think it's that expansion into the kind of vertical markets that will be most useful for COVID-19. All right. So we have another question. So on the more frequency slide, just so I guess high band frequencies are better suited to more densely populated areas. So yes is the answer to that is so you could use for a more densely populated area. We would typically try to have a smaller cell, because if you're more densely populated, a smaller cell will end up covering fewer people, and the fewer people will generate less data. So if they're generating more data than a smaller cell, so if a cell can handle like data from 10 people, then obviously in a more densely populated area, 10 people are going to be in a closer group. So the high band frequencies would really only work in a small cell. So they are by definition probably small cells, but I think it is important to note that the lower frequencies can also be used in small cells. So so there's no reason why it's only high frequencies that you use. So the power that you put out of your base station also affects the area. So yes, so the high frequency is just small cells, but actually you could use any frequency for small cells. So there is a what's quite an unusual question. Now we've worked for 5G about the impact of beams to individual users and higher radiation levels. I'm not an expert in that area, but there is like lots of information and stuff that's out there really sort of explaining 5G and how things like that aren't issues. And as I kind of highlighted, there's a lot of 5G spectrum that's pretty much in the same area that's used for 2G, 3G, and 4G. Okay. So next question is line of sight to antenna requirement for maximum efficiency of 5G range limitation and number of antennas required. So the sort of radiation effects and how that's managed. So 3GPP, they define the 5G standards, and as part of that, they also define how much power comes out of a 5G base station. So there's limitations on that that can happen, and if we have like a small cell, like in those dense urban cities, they are a lower power and have lower power limits on them. And then when we get to the larger sort of macro cells that are covering a wider area and are typically higher up and situated somewhere more rural, they do have like higher power limits. But the actual power that comes out of it and the sort of radiation pattern that comes out of that, that is all standardized, and there's conformance testing, and you have to meet a whole bunch of requirements before all of that equipment is put in a 5G network. So effectively, we kind of rely on the standards. We use the standards and the conformance testing to ensure that we understand exactly what radiation is coming out of 5G networks. Okay. So I think that answers all those questions. You said there were a few more in the chat. Or did you copy them all across?
They're all copied across, so we've covered all the questions. We've received some lovely comments in the chat just saying thank you to you, Claire, for a fascinating and informative session. People are pleased they signed up and have attended, and it's been really well narrated and insights. So I know we scheduled an hour. We've got 5 minutes left. So if anyone's got any final questions, feel free to post those in the chat. If not, we'll say that that's perfect timing, and we can give everyone just a couple of minutes back before maybe their lunch break.
Cool.
Just pause, see if we get anything.
And the noise from my open window to stop me turning melting was fine then.
Yes, no noise at all. So I'm glad we didn't have you fainting through heat stroke. No, just lots of thank yous. So yes, a huge thank you, Claire, from the CWT partnership, everyone who attended live and through the recording. We really appreciate you going through this with us. So with that, I'd like to wish everyone a good day, and once again, thank you, and we'll see you at the next CWT session. Thanks, bye.
Great, thanks everyone, bye.